Okay, let's start the last session. I think everybody online is people that already have been here a few times, so I'll skip the first part if nobody has objections, and we'll just go through the last bit. So here we are basically trying to define something for the states and processes. So we're basically skipping that intermediate layer of information granularity that we don't know yet how to do, but we have probably found the right axioms, well, the right approach for defining states and processes. And this is stuff that we are slowly adding to the book, and hopefully we'll get finalized in the next, I don't know, 6 months, whatever. So this is sort of the summary slide. I'll go through it so that you have a general picture, and then we're going to go and look at the detail for each of these pieces. So the point would be to define spaces of ensemble. So a general set of axioms that ensembles must follow to make sense. Both classical and quantum mechanics would be particular instantiation of these spaces of ensembles, and they should be able to be reconstructed in some way. So the first thing that an ensemble must allow us to do is to mix them. So we need to be able to take two ensembles, define a probability for one, and create another ensemble. And this gives us a convex structure. In general, a convex structure is not exactly a linear structure, it's not linear, not exactly a vector space, but essentially because you don't have an inverse. And so if you assume that there is a unique complement, meaning that if you fix E, if you fix E1, and if you fix P, then there is a unique E2, then you essentially get a vector space structure. And both classical mechanics and quantum mechanics satisfy this axiom. It's not clear whether physics must satisfy that axiom. So I have no idea whether to impose it or not. So for us, right now will be an extra axiom that you can. Then the idea is that ensembles also must define an entropy, and that the entropy must be a strictly convex function on the convex structure. Meaning that if you take two elements and you mix them, then the increases entropy from the entropy of the mixture and the average entropy that they have, it has to be greater or equal to 0, and it's 0 only if the two elements are the same. You also have an upper bound. And so the idea is that this difference is limited by this lower bound and upper bound. And what this gives you, it's a semi-metric. Unfortunately, I haven't found much literature on these things because it's kind of a matrix, but it does not satisfy the triangle inequality. And this thing is also in both classical quantum mechanics and quantum mechanics will reduce to something that is already exists, which is called the Jensen-Shannon divergence. What happens is that because this thing is strictly concave, the Hessian of the manifold of the entropy is going to be a negative definite tensor. And so if you put a minus sign, this becomes a positive definite tensor, which is follows all the property of a Riemannian tensor. And this becomes a metric for the space of the ensembles, which maps to the Fisher-Rao metric. So you basically, the idea is that you recover sort of the information geometry. And the idea would be to show that then this also becomes the inner product in quantum mechanics and the symplectic form in classical mechanics. This upper bound, so this basically works on the lower bound. On the upper bound is that you can define a notion of orthogonality. And from that, you can define a notion of subspaces. You can define orthogonality of subspaces. You have a way to define the probability measure and some sort of dimension in terms of this. And that with those things, you basically recover a more general form of probability that I sort of skimmed, like briefly explained yesterday. And recovers also classical probability. So the idea would be that from only these two notions, we will recover all the linear structure, all the geometry, and everything that is there both in classical mechanics and quantum mechanics. That's the goal, and it's very promising. And what we're basically showing here are the bits and pieces that we have. We still need to do it, but it's already working well in many cases. All names are placeholders, so if you don't like a name, it's okay. I don't like them either. We'll have to figure out what the good names are, and I'm more interested right now in the defining and understanding what these concepts are and how they work mathematically, and then it will dawn on me or on us later what is the right name to call these things. So first of all, we're going to have a set of axioms to define mixtures and convex spaces. And so the first axiom is just that the state of a system is represented by an ensemble, which represents all possible preparation of equivalent system prepared according to the same procedure. And the set, and then again, this is the set of all possible ensemble for a particular system is an ensemble space. And again, formally, the ensemble space is a T0 second Cantor topological space where each element is called an ensemble, because these are things that we have to be able to define experimentally. So as we saw before, it has to be a second Cantor topological space. We have the argument that we saw before yesterday as to why we want it makes sense to use ensembles as the starting point. And the idea, again, is that pure states are idealized ensembles, and only what we can prepare in practice are essentially ensembles, and therefore the ensemble is a basic object for describing the system of the states. We have three cases that we want to recover. The classical discrete is that we have countably many pure states, and an ensemble is just a probability distribution of that can be understood as simply as a series of coefficients that sum to 1. We have the classical continuum where the phase space is a symplectic manifold, and the ensemble is just the continuous probability distribution over that. And in quantum mechanics, the set of states is the projective complex Hilbert space, and the ensembles are the positive the semi-definite Hermitian operators with trace 1. This is basically the mixed states. And so the idea is that we want to be able to recover all these things and understand and make sure that everything that we say is valid for all these things. The first axiom that we have is, the second axiom that we have is the axiom of mixture, that basically says that the ensemble space is equipped with an operation plus that takes a number from 0 to 1, two ensembles, and gives us another ensemble. This is called the mixing. And we note it like this, where P bar is 1 minus P. We're going to have so many 1 minus things that it's convenient to put a bar. And these are the axioms that you need to have. You need to have a continuity. You need to have an identity, meaning that if I mix 100% of the first ensemble with anything else, I always get the previous ensemble. If I mix an ensemble with itself, I get the same ensemble. The order of mixing does not matter. And then you have an associativity that you need to express with this mixing, and it becomes a little bit cumbersome, but that's basically it. And so this mathematically is called a convex structure, and the classical probability distribution and quantum density operator have a convex structure. You can actually do these operations and they satisfy all these axioms. With this, you can start defining things that are a little bit useful. So whenever you have a mixture, you can call the sum of everything the mixture, and we can call each element a component of the mixture. And then given two ensemble, you can say that something has a common component if you can find a third one, such that both the first and the second are a convex combination of the third. And the third would be the common component. And two elements are distinct if you can't find a common component. Essentially, there is no other ensemble that is smaller inside both of them. And all of this can be represented geometrically, because what happens is that if you have two elements, A and B, then the mixtures are really represented by the line that connects them. and lines closer to A have a probability, points on the line that are closer to A have a probability of mixture that is closer to A. So this would be 100% A, this is 75% A, this is 50% A, and you're really linear with respect to the line. So things work well. And this would be the diagram for our common component. Now, this C would be a common component of A and B because we can find a D and an E, where A and B are a mixture of D and C, and B is a mixture of E and C. So this is how it looks geometrically. And with this, you can start proving some theorem, and hopefully there are more things that we can prove. So if we have three ensembles, if E is distinct from a mixture of E1 and 2, therefore there is no common component between E and a particular mixture of E1 and E2, then you can show that it's distinct from all the mixture of E1 and E2 and from both E1 and E2. And this is the notation with the distinct with this orthogonal symbol. However, if E is distinct from E and from E1 and E2, it is not necessarily true that E is distinct from a mixture of E1 and E2. And again, here you can make a little diagram. This is E1 and E2, this is E, and you can say that it's distinct if you have a common component, if any point here, let's say A, has a common component with C, or actually, if it has a common component with B, then you can find a C such as that you can make this triangle. But then, if it's the case, then it has a common component with here as well. And so you can sort of do it geometrically and then write the proof. So again, you can start doing things like this that are sort of cute and needs to do. So this is the other axiom that we were talking about before to actually get to vector spaces. You can define a complement if it's the other thing that sum to E1 gives you rho. So we say that E2 here is a P complement of E1 towards rho. And you say that the space is complemented if all the P components are unique. So if I fix the final mixture, one of the elements of the mixture, and the probability of mixture, the mixing coefficient, then the other, there is only one other ensemble that gives us the mixture. And what is an interesting result is that an ensemble is complemented if and only if it is a convex subset of a real vector space for which the mixture are the linear combination. So really what can happen in a convex space that you could have C and B, and you are mixing towards A, and then there is a point here where they become the same. Therefore, if you start at this point and you go backwards, you could end up in two different directions. And that's exactly what does not happen if you are in a vector space. That once you have defined 2 points, there is only one way to go backwards, to go in and find the elements that you could be mixing. And so both classical and quantum mechanics are complemented, but at this point, it's not clear whether this is a necessary axiom or not. So at this point, we could imagine that a more fundamental theory of physics would have to relax this axiom, and the space of ensembles are more complicated. You still have a convex structure, but you wouldn't necessarily have the vector structure. So for this part, ensemble mixing provide a convex structure, and the invariability of the mixture recover the vector spaces, not convex spaces. And there are probably other results that would be nice to tease out, and there are probably books on convex spaces. There actually not so much research on the type of things that we do. Convex spaces are mostly used for optimization, and we're not using it for optimization. So the type of things that people do on convex spaces are completely irrelevant for the type of stuff that we want, but there should be other things that we should be able to get. And one of the things that we need to get is how to get to topological vector spaces. Okay, so that was the one set of axioms. The other axiom is about the entropy. And so we first define an entropy that is only defined on the coefficient, which is essentially it's the Shannon entropy defined on the coefficient. And then we have the axiom that tells us that each ensemble space is equipped with a function called entropy. and the function has to be continuous. It must be strictly concave, meaning that if we have a mixture, the mixture of two elements has to be greater than the average of the expectation of the mixture of the elements themselves. And the equality hold only if the two elements are the same. And this is important because it tells you that entropy knows when two elements are the same. So the entropy knows the equality of elements, which is important when you are going to have to define the geometry, because distances and so on must know when things are equal. And then we also have an upper variability bound, meaning that if we have two ensembles and we mix them together, the maximum increase in entropy that we can have is when these two elements, we say they are disjunct. There is nothing in them that is the same. And at that point, the increase in entropy must be just the choice of which element I've picked. And so the increase in element is bound by the entropy of the coefficient. You can't have an increase that is greater than picking which ensembles you have just with the coefficient. And I think that's it for this. There is this difference in quantum mechanics between let's see. Okay. This disjunct in classical mechanics corresponds to essentially having two distributions that have disjoint support. When two distributions have disjoint support, the entropy is going to basically go up only by the choice of the two. And in quantum mechanics, the disjunct ensemble corresponds to density operators living in orthogonal subspace. So in both cases, disjunctness is an orthogonality, because if you made an inner product of on the probability distribution, which is typically the integral of the product, you would get orthogonality for things that are disjoint support. So basically, what we're seeing already here is that this notion of disjunctness from the entropy has a sense of when things are orthogonal in the space. And orthogonal here basically means maximum distance in terms of entropy increases. So all these things are related. Then we can say that an ensemble is reducible if distinct, an ensemble space is reducible if distinct ensembles are disjunct. That is, that if two things do not have a common component, then they also make the entropy go up in a maximal way. And this is essentially the difference between a classical ensemble space and what happens in quantum mechanics. In classical mechanics, distinct, meaning not having a common subdistribution, is the same as disjunct. You are, if you are distinct, you are disjunct. If you are disjunct, you're always distinct. Now, what happens is that in quantum mechanics is that that's not the case. All pure states are distinct because there is no finer ensemble that you can tease out between them. But only orthogonal states are disjunct, only the ones that are opposite positive of each other in the Bloch sphere. And so essentially, all the difficulty in between classical mechanics, the fact that you have different probability, that you have entanglement and all these things, is just the fact that distinct is not disjunct. And we, from the classical side, we really tend to conflate these two in our mind. And then if you start saying that these are two different things, that not having common distribution does not meaning that you are on separate spaces, that things become simpler to understand once you put everything in the same picture. And so there are two other axioms that relate disjunction and distinctness that I don't think they're axioms. I think that they should be able to be derived from the previous axioms, but I just don't know how for now. And so I'll just put them as axioms for now. One is that disjunctness always implies distinctness. So if things maximize the entropy when mixing, then there should not be a common component. That kind of can be justified by the physics, by knowing what the entropy is and so on. But I still think that there should be a theorem there to prove. I don't have that yet. And then also that mixtures preserve disjunctness. So if you have something that it's a mixture of two things, and then a fourth thing is disjunct from E1 and E2 only if it's disjunct from E3. So basically, if E4 does not have anything in common then E1, then it can't have anything in common with E2 and E3 as well. They must be all completely different. And again, I do think this should be provable because there is a sense that the shape of the Shannon entropy has these vertical asymptotes. And so once you have a vertical asymptote, you can't really go farther away. So you should be able to say, you are at the edge, and therefore you can't find common components, because for common components, you would have to be further and so on. But I still don't know how to put this in. So that is an area that... And then what is this? And this is again something else that in principle should be provable, but I don't have. I'm a little bit confused. P then in chance. Yeah, it's not gonna matter. But this is something that again, whether there is some interplay on the convex structure and entropic structure that can be teased out, and some stuff that I'd like to. So, okay, the problem is that we have this entropic structure on top of the convex structure, and the disjunctness allows us to reconstruct orthogonal analysis. And now the idea is that with just these things, we can start proving things that are interesting. So in classical mechanics, you have a link between the entropy and the logarithm of the count of states. You have something a little bit the same in quantum statistical mechanics, and we want a generalization of this relationship that does not even know whether you're in a classical or a quantum setting. And what we can prove is that if you have the two elements, E1 and E2, and S1 is the entropy of the first, and S2 is the entropy of the element, and you make a mixture between them, and you say that S is the mixture of that, then what you find is that the exponential of S is less or equal to the sum of the exponential of x1 minus x2. And the equality is there if and only if the probability is it's essentially 2s1 over 2s1 plus 2s1 s2. And the point is that from just what we had before, you can find that this exponential of the property, the exponential of the entropy, has this key property, and this is the key property that allows us to justify that the entropy is the logarithm of the count of state or a measure, because this is exactly what we're seeing here, is that the exponential of the entropy is essentially subadditive, and the additivity is when you can actually construct a measure, when you have an equal. And these are just going to be the weights that you would have. You would have the mu of 1 and the mu of 1 plus the mu of u2. And the proof is extremely simple. It's just applying definitions and doing a maximization, and it just comes out. It's beautiful how it comes out. And so you can, once you define something called a convex hull, which is the space of all the mixtures, you can start defining things on this convex hull, and you can define something that is kind of looks like a measure. And so you can say that once you have a set of ensembles U, you can define something that we call for now the dimension as the supremum of the exponential entropy on the hull. So you take essentially the element in the convex combination that has the highest entropy, and then you do this exponential entropy thing. And what you find is that this is a set function. It's not really a measure because it's not additive. It would be a measure, it would be additive, but it's non-negative, it's monotone, it's a subadditive, and it's additive on the sets that are perpendicular. So we're essentially recovering the fact that the entropy of a uniform distribution is it's less or equal to the logarithm of the dimension u, or the measure of u. It's just that this element is not necessarily active. And again, the proofs of these things are trivial, and with this definition, then you can go in sort of non-additive measure theory. That's what I'm doing right now, and start getting theorems out of there and things that are useful. And the fact that quantum mechanics needs a non-additive measure, you can sort of see by comparing the measure of states in these cases. In quantum mechanics, the measure of the entropy of each pore state is 0. Therefore, this measure for each pore state is 1, and therefore we can interpret this as a count of states, which would make sense. In quantum mechanics, we're saying that each state corresponds to a count of one state. If you have two orthogonal elements, then the maximum mixture is here in the middle, and it's going to have entropy 1. Therefore, the measure for two elements that are orthogonal is 2. But if you take two elements that are not orthogonal to each other, like A and C, then the increase in entropy is not going to be 1, it's going to be less. It's still going to be the measure, then it's going to be less than 2, which is going to be less than the measure on each element. But then essentially the count of states for two elements that are not orthogonal, it's a subadditive. It gives you fewer states. And one reason that this actually makes sense is by comparing what happens on the count of states in the 3 different cases. If you have a discrete space, then each point counts as one state, and you have an entropy of 0. But you have an infinite, finite continuous range, meaning that you have infinitely many elements. Then the measure is infinite and the entropy is infinite. If you have a Lebesgue measure, then the size of each point is 0, and you have a minus infinite entropy. This is something that we said in classical mechanics. This is where you have a problem because you have an infinite entropy. But then if you have a finite continuous range, you have something that's finite. And what happens with this quantum measure is that both the point is finite and also the finite continuous range. Because if you take the sort of the entropy associated with the whole surface, the highest entropy that you can reach is still the element at the center, and the still element of the center has 1 entropy, so it's finite. And so what happens here that I find that is interesting is that there are 3 things that you would like to have as a condition on a measure of states. You would like every single state, every single point to count as one single case, so the measure would be 1 on a single point. You would have that finite ranges carried finite information, so you would want the entropy, the measure, the count of states for a finite range to be finite. And you would like the measure to be additive for these joint sets. If you have 2 sets that are separate, then you put them together, you sum them, and you get the sum of the states. And what happens is that these 3 they can't stay together. You have to pick 2, because if you say that I have a single point is 1, and my measure is additive, of course, the finite range will be infinite and so on. And what happens is that the discrete classical case sacrifices the second constraint. The Lebesgue measure, the continuous case, sacrifices the first one, and quantum mechanics sacrifices the additive. And so this kind of makes sense in a general sense why you would have that, and this is something that we are exploring in more detail. So the takeaway of this is that the upper entropy bound leads to a natural notion of size on the side of a dimensional sets, which recover the statistical mechanics relationship in the general case. The notion of size is generally not additive because there are essentially like in quantum mechanics, you have this notion of contextuality and non-single decomposability of the ensemble that leads you to this. And it is still additive in this joint set. So the measure is always additive in quantum mechanics because all distinct are disjunct. And in quantum mechanics, becomes disjunct become orthogonal, so the measure becomes additive on orthogonal basis. And so when you're making a measurement, you recover that this is actually that actually works. Okay, so we got a notion of measure out, and now we want to get to a notion of geometry. And I don't know how much you know about this, but in general, in a classical probability space, you can define this tensor, which is called the Fisher information metric. It's defined like this, and it gives you essentially a geometry, a Riemannian geometry on the space of statistical distribution. So you can define a notion of distance, you can define geodesics, you can do all the things that you do in GR, you do them on this thing. There is also a quantum analog, which is called, I don't know how to pronounce this, is this Bure or Bures, I don't know, but it's defined with, again, the Hermitian form and so on, and it can be shown that this is the quantum equivalent of the Fisher information metrics when you do some kind of manipulation. All these pieces are taken from Wikipedia, so they are completely like known elements. And so the idea is that we want a generalization of this. We want to have our metric tensor without even knowing whether we are in classical mechanics or quantum mechanics. And this is how we do it. Because we have that bound, we can define, given to ensemble, a mixing entropy, which is essentially the increase that we get from considering the entropy of the two elements and the entropy of an equal mixture. And you do find that this, for the bound, has to be bounded from 0 to 1. 0 if they are the same elements, and 1 if they are disjunct, if they are orthogonal. And it's a symmetric because it does not satisfy the triangle inequality, and it generalizes the Shannon divergence, Jensen-Shannon divergence. So we have a general definition for something that is already a known object. And what you can do now, we need a little bit more constraint to be able to define our geometry. We need a vector space. So we need our space to be complemented, and we need a differentiable space. It's probably not required, the differentiability. It's probably we can recover it from the entropy. But again, for now, we just add it because we don't know. And this will give us a vector space with a differentiable structure. And once we have that, we have a notion of neighborhood, and therefore we have a notion of tangent space. And we can define the norm of the variation based on the mixing entropy that we had before. And we can then define a metric tensor in the typical way. When you have a norm, you can get the square of the norm of the sum minus the square of the individual norm. And we put a 1/2 there as well. And the idea is that this recovers the geometric structure. You can show that this is essentially minus the Hessian applied to the variation, and that the metric tensor is just minus the Hessian of the entropy. And this again works, as I said before, because the entropy is strictly concave. Therefore, this is going to be a tensor, rank 2 tensor that it's negative defined. And if you put a minus sign, it's going to be positive definite, and therefore it's going to work as a Riemannian metric. The proofs, again, are trivial. Literally, this is the proof. It fits in a half a page of a slide, right? And half a slide. And again, in all of this, the game is to find a definition that gives you the things simply. So the fact that I can get to this result very simply, it really tells me that these are the right definition, that things work. And then you can show that specifically for a classical ensemble space, that thing that we have defined is the actual Fisher-Rao metric. And again, this is the proof. You just put in things and calculate, and that's what you get. I don't have the calculation for the quantum case because I don't understand the quantum case that well, but it's it should be the same thing. We should get the same thing. And one of the things that is a problem for me is that this notion of differential geometry is limited to manifolds. So when you do the Fisher-Rao matrix, you take a finite set of parameters. And I'd like to do the define things more general on the full space. So I kind of need a notion of tangent space on an infinite dimensional space, which I don't have right now. And this is another side project that I have, and I have a couple of undergrads that are trying to help me figure out for the proof. It's really trying to create a better definition of differential manifold that one works better for physics, that recovers the ideas that Newton had, the little things that we do when we explain what integrations are. Because right now, the way that mathematicians have developed things, they've developed them in a way that it's first does not make sense physically, because the way that the way that vectors are defined are basically as a derivation. So a vector here, it's essentially this operator here that is applied to a function. And that's when people talk about tangent space, that's how tangent space is defined mathematically. And it, of course, physically does not make sense. Velocity is not a derivation. The momentum would be a covector, and it's not a function of a derivation. The issue also that derivations in general for us depends on the unit and cannot be summed. If I'm deriving with respect to r and deriving with respect to theta, well, these have different units. I can't just sum them. So even saying that that this is the basis, it just doesn't work. It doesn't work. And then there is a sort of a double dipping, because the differentiable structure is defined on top of the Frechet derivative. And so it has a notion of differential. But then when you go on top of the differentiable manifolds, you define differential as functions from a vectors to a real number. So you have a different notion of differential, and that doesn't make any sense. So what we are trying to do is essentially make the case that the notion of differential reducibility is what gets the differentiable structure. And we want to define a differential as essentially a sequence of vectors that goes to zero, but go to zero in a way that there is a particular direction that they're going to zero. And this is the tangent vector. The tangent vector is the direction where your differential is going to zero. And then, once you have this structure, the idea is that you have a space of time, you have your time, your space, and your temperature, and these are all your spaces, and you have a function between them. And then you have this space of differential of things that become small. And these functions are differentiable if you basically have a map that whenever you take a differential from here, maps to another differential here. So we recover the idea small things are mapped to a small things with a particular direction. So I'm going to zero nicely in one case, I'm going to zero nicely in the other case. And so the velocity just becomes a map between the differential in time and the differential in space, meaning the velocity is the thing that if I give you a small change in the time, you're going to give me the small change in space. And tensors can be understood like that, and we're trying to get the structure. And the point is that all of this should only care about the vector space structure and not care whether that vector space structure is finite dimensional or infinite dimensional. Our notion of derivative already tells you that if the derivative exists, it must be linear, which is nice to have. And we're now trying to prove whether all the other conditions that we should have hold, but when you do calculation, the things are basically the same. I'm not going to go into talk about the details of this, but that's basically what we're trying to do is to make sure that all these things work and recover all the standard notion, and that can also recover the notion of differential topology, the forms, and the Stokes theorem, all this. So this is the part that we're going to do. And I think that once we have something like that, then we would really have a general theory, because we could start talking about these symplectic and Riemannian manifold extended in an infinite dimensional space. And this is the thing that I think we need to do the good extension on field theories of the things that we saw in the first lectures. We need a space that sort of behaves the same way, whether you have finitely many or infinitely many degrees of freedom. So, but this is yet another direction, which is sort of related, but sort of tangent, but it's still part of physical mathematics, because it's, again, trying to rederive all this notion of differentiability from physically meaningful ideas. Then we can go and proceed with subspaces. We saw that we need, from the notion of disjunctness, we can go and derive the subspaces. And so that's what we are going to do. And the other thing that we would like to do is also recover the notion of points. And if you imagine that we want to say that the ensembles are things that we can actually prepare, the ensembles themselves do not, as ensemble in classical mechanics, an ensemble at a particular point at position of momentum does not exist. And so the points are not really ensembles, the points of the space and the points of position of momentum. And so since the only thing that we are given by the mathematical structure are the ensembles, we need to have a construction for how do we create and we find the points. And this is one of the things that we are going to use, is to use disjunctness to define subspaces and then find limits of these subspaces that then corresponds to the point. So there is a lot of mathematical trickery that needs to be figured out to make this thing work, and we're still not fully there, but we do have the pieces. One of the things that we were able to rediscover, because once you make the calculation, of course, you find other people that did similar things, but you can never find them before you actually have finished the thing. So if you have a set in general, and you have a relationship, a binary relationship that is symmetric, meaning that you give, you have two elements. For each two elements, you get a true or false. And if you swap the elements, the thing is the same. What you can do is define a complement based on that relationship. Then you basically take all the elements that have the relationship with all the elements of U. And again, this is going to be a notion of orthogonality. So orthogonality is a symmetric relationship. And the orthogonal complement is the set of all the elements that are orthogonal to the set U that you give. And but here we don't know that this is orthogonality, right? We just know that you have a symmetric relationship, and you can essentially show a lot of properties just because of that construction. And if you add the fact that the things is irreflexive, meaning, for example, for orthogonality, you're never orthogonal to itself, you recover the last two properties that you have. And these are the properties that you really need from a subspace. And so the idea is that with that property, you can start defining all those sets for which their complement of the complement is equal to themselves. And those are going to be your subspaces. And again, if you have a subspace in a vector space, the subspace is the orthogonal complement of its orthogonal complement. So instead of using that as a property, we use that as a definition, and then you can essentially create the lattice of subspaces just from that. And you can recover the same idea, and so you say disjunctness is a reflexive and symmetric relation, and then you can create the space of ensembles, and you recover the correct notion. So in classical case, a subspace is going to be the set of all distribution with support within a set U. Those are going to form a subspace. And in quantum case, the subspace is a set of density operator that live in the same subspace of a Hilbert case. So the point is that this gives a notion of subspace that it's more general, that works in the general case, but it recovers the thing that we want to recover in the two subcases. And then the issue here is now that we need to recover the topology of the base space. So the idea of recovering the points is, again, finding subspaces that become smaller and smaller and smaller and smaller. And in principle, there should be a construction to do that. And we're still in the process of figuring that out. And one of the things that connects to what Tobias was saying before is that the Hilbert space itself does not have enough information to recover the space. So if I give you the subspace, the Hilbert space of the lattice of subspaces, you wouldn't be able to tell whether you are from the space of integral function of R or the space of square integral function of Rn. There's just not enough information. And if we have the Schwartz space instead, the topology would be different, the limit would be different, the subspace structure would be different, and then we're going to be able to recover this. And again, this has sort of makes sense because the Schwartz space means that all the expectation of all the polynomial of position momentums are finite. And so those are the things that we can actually prepare and measure experimentally. So there are these level of detail that needs to be fixed, but hopefully we can fix it. And then, as I said, we can define the pure state as something that a sequence of subspaces that become smaller and smaller. There are a lot of tricks here that I haven't fully understood. I kind of know that the thing has to work exactly how it works. It's still to be determined. But anyway, we have a general notion of subspaces from ensembles that come from this judgments. And also the geometry of vector spaces, the inner product and orthogonality is also uniquely defined by the entropy so that we can recover this notion from them. The last thing that we need to recover is probability and measure theory. And in classical probability, the space is defined by these three things: by a sample space, by a sigma algebra, and by a probability measure that has to be additive. This does not work for quantum mechanics, even though I don't know how many people in the foundation that try to put these things. It just does not work because of the classic problems of Bell type inequality and things like this. Like you can't recover the classical quantum mechanics from the space of this distribution. And so we need a different way to define a probability measure. And here the idea is that I have an ensemble, which in principle is a statistical distribution. I have a set of other ensembles, and I'm looking for the element in all the possible linear combination in that from the ensembles in A that maximizes the probability, the mixing coefficient that I've put in. So I'm basically trying to look for the mixing coefficient that is the biggest within all the possible things that I could do. And I have to do a supremum because that maximum might not actually correspond to an element in the hull, so that you might have a limit, and I still need to put to get that P, so you have a supremum, which makes the things a little bit more complicated, but that's how it is. And of course, what you find is that you have two ensemble. This measure, the set function that you have defined, has to be different because it has to be different, at least for those two elements. And so given a set of ensemble, the probability that you get is the biggest mixing coefficient associated to the biggest component of the target ensemble. So you basically have an ensemble, which is going to be a probability distribution. You have the ensemble constrained on a support, and you're going to try to find the one that you're mixing with the biggest biggest mixing coefficient, and that will correspond to the probability when you do the calculations. What you can find is that this set function that we find is non-negative and it's bounded. So it's not like when you're extending probability theory using a Wigner function that you get negative probability and you don't know what the probability is. Here you do get something and still a mixing coefficient, so you always know what it is. It's monotone, meaning that if you increase the size of the set, the probability can only go up, it cannot go down. And it's subadditive, meaning that if you have two disjoint things and you put them together, then the probability can only increase up to the sum of the probability. It is not additive in general, and what you can find is, again, you can recover it when these two things are disjunct. And the way that you do it, I'm still working on the details, but you basically find a subset of subspaces, which essentially is going to correspond to a context in quantum mechanics. It is going to correspond to an orthogonal basis for a discrete set of orthogonal state, and it will correspond to a spectra of a Hermitian operator in the case that you have sort of that your points are dense, that you have a continuum. So hopefully it would be ideal to connect all these things to quantum logic so that we have another thing that we can bring in. But that's sort of the point. It's that we can define a general non-additive notion of probability that is physically motivated and works for both classical and quantum mechanics, and recovers the notion of probability in the special case. And here the thing that is really fundamental are the mixing coefficient, and they will correspond to the probability only when you are in these orthogonal context, because then the probability that you get out is the same thing as the mixing probability. So how you mix things is exactly the same how you get things out. And this is exactly what doesn't work in quantum mechanics, because you can mix things from different contexts, and then the probability that you get out is not the same as the mixing coefficient that you put in when you did the actual mixture. And so this all makes sense. There are other things that are missing. There has to be a symplectic structure that it's linked to coordinate invariance. I don't know how to do that. There has to be a notion of composite system, therefore product spaces. It's not clear exactly. I haven't even looked at that. I have started looking at quantities, and quantities are just going to be linear maps of ensembles to real number, and this should correspond then to what you expect in classical mechanics and in quantum mechanics. And then the idea of creating a theory of processes as again linear ensembles of maps. I give you two ensembles. I give you one ensemble, and I give you the final ensemble, and this is linear in terms of convex combination. And then the hope is that if we have all of this done correctly, field theories should live inside the same space. It's just that when you go and find the points and look at the subspace structure, the subspace structure is a lot more complicated because the points are function spaces instead of just the manifolds or infinite dimensional manifolds. It's going to be more complicated. But the point is that all of this starts with the finite, because the ensembles represent things that have everything finite. The finite entropy represents finite objects. And so everything that we deconstruct later, all the points, they are these infinitesimal, but we always have a handle of what is finite. And therefore, we know the infinitesimals is found by taking the finite thing and chopping it up into smaller things. It's not the case that we start with infinitesimal things and we put them together, and then we have to find which things actually converge. So we already have the notion of convergence because we start from there. And so I hope that would make the job of looking for how to make field theory work decent, because we know all the finite constraints, hopefully. That's the idea. And I think that's it. So the point, the main idea here is to construct a general theory of states and processes with minimal requirement on essentially using the idea of ensembles as entropy. The idea is to create concepts that work for all theorying, and there is also lots of interesting mathematical work to do to make this thing work. So it's gonna keep us busy for a while. But this is the piece that right now I feel it's the most interesting, because it ties in a lot of things. It ties in vector spaces, it ties in the notion of distance, differential geometry, set functions, non-additive measure theory, probability theory. It's the space that ties everything together. Like when we looked at classical mechanics, we saw that we could understand classical mechanics from different points of view. And it's always clumsy because you have to translate one point of view in another. Like when you're doing differential geometry, you're not doing probability theory. You have to translate the two. When you're doing information theory, you're doing something a little bit different. And it always feels clumsy. And this is, I feel, the structure that puts all these things together. We can see at one thing, and then from that one thing, we see how it connects to all the other things. So that gives me hope that that's the thing to do. So that's it, and we can open it up to questions. I think there was already a question. I've heard I heard it said that geometric algebra is the right language for physics. Does it have the same definitional issues you mentioned? So there is a lot of things in algebraic topologies, and the algebraic topology is always. Oh, so there are two things there. So if by geometric algebra you mean what is it called?
Like Clifford algebras.
Say it again.
Clifford algebras.
Yeah, Clifford algebra, exactly. So the Clifford algebra, to me, is mixing things that you shouldn't mix. Because what the Clifford algebra does, it takes essentially the algebra of the differential forms and puts them together into a single thing. So a differential, let me see if I can get the slide. I didn't talk about it. So let's see, I should have this slide over here. Okay, so for me, here's how we want to recover differential forms. The point is that differential forms are things that work at the infinitesimal level, but then the thing that we do, that we work on, are always finite objects. So, for example, you have mass density. Mass density is a differential form, but what we measure is not really mass density. What we measure is the mass on a finite volume, right? And so we have a map from the mass, from the volume to the mass. And then we assume that the mass is additive over disjoint region, which is also not always the case, but we assume that that's the case. And then we say, okay, we take limits, as I was saying, we make this volume, we make a sequence of volume that are smaller and smaller. So we make all this sum become bigger, bigger, bigger. And then for us, the mass density is that. It's the limit of when we made the volume small, and then we take a contribution that's the best amount. So for us, we want to be able to define a differential forming like that. And this works for everything else. So magnetic flux is a function of a surface. And then you say magnetic flux is linear, is additive over disjoint region. And then B, the magnetic field, is the magnetic flux in the infinitesimal surface. And the same thing for the work. Work is a function of a path. And then we say the path, the work is additive to the result. So the point is that we would like to just say all these objects are derivatives of one thing to the other. That's why we want this generalized notion of derivative, to just even say these things are strictly derivative. These are going to be function space, vector spaces. So it's just another derivative for us. And these are the form. This would be a one form because it takes a line element. This is a two form because it takes a surface element and so on. And what you do in a Clifford algebra, you put all these things together and you define sums that include the one form to two form. And that physically, to me, doesn't make much sense. I'd rather say that I have a one form and two form, because there is no sense that I can sum these two things. First of all, just because of units, how does that work? And then even when I do the integration, I can't do the integration in the same way. One has to be done on a line, and the other one is on a surface. So I see the Clifford algebra, the idea that you create these products among all these different hierarchy of forms as a good mathematical way to compact things, but I think it's obscuring the physics because you're not realizing that the thing that you call one object is actually physically multiple objects. And one of I'll finish it and then I'll let you go. One of the thing that I see people get excited with Clifford algebra is that you can have a compact way to put E and M. But the thing is that you have a better way to make a compact E and M by doing things in 4-dimension, and you get a lot more physical insight, because in that way you really see how the form of the magnetic field and the form of the electric field that in standard 3-dimensional spaces are two different things. One is a two form and the other one is one form. You put them together and they become a 1-2 form. And that's where you understand that those things are actually part of the same thing. And so there is a much better way to do the thing that the people get excited about Clifford algebra. So, and again, I said this to another person. This is my view now. If somebody showed me a way, oh, but you can represent these things physically much better, then I would completely change my mind in a second. I said, oh, okay, now I see.
Okay, thank you. That explains a lot. I was going to ask about the electromagnetic field.
Oh, very, very good.
Are you referring to the 4-dimensional representation? Like, what can I look up? Which one are you talking about?
Say it again?
You were saying that you could represent it in 4 dimensions, and we try to say everything is a bivector if you represent it in 4 dimensions?
Correct. The electromagnetic field itself is a bivector. Yes.
Where can I look this up? What's the name of this formulation?
Say it again?
Where can I look up this formulation? I'm curious about it.
It's any GR textbook. It's any relativity textbook. It's a relativistic way to see it.
Okay. So you are okay. Thank you.
Not only it's a closed two form, and so now you have the potential as a one form, which is the standard 4-dimensional potential that you have in relativity. So this actually is a perfect example of how sometimes mathematicians generalize things that are nice and cute mathematically, but they're not good for physics.
Thank you.
Can maybe someone explain to me some details? I've heard of Clifford algebras, but I never learned about them. I've heard about geometric algebra, and for me the only advantage was that you get rid of the cross product, which is like extremely ugly because it only works with 3 dimensions, and it has like an arbitrary orientation that you need to choose beforehand. So, but as I see it, so you can multiply 2 vectors and you get, well, for a cross product you get a vector, and in geometric algebra you get a bivector, which makes like much more sense. But you don't need maybe to add bivectors and vectors and scalars. Maybe there is some other kind of operator like this, like the OR.
The wedge.
The wedge. This is so I need to learn this stuff. How is this called? This is like 2 forms that this is the wedge product operating on forms and gets like 2 1 forms and gives me a 2 form or something like that.
It gives you a form that is of the order of the sum. So if you do a wedge, an exterior product of a 1 form with a 2 form, you get a 3 form.
Okay.
And the way that you should think as form is exactly this. It's a linear function of the parallelepiped that you're getting. So a 2 form is a function of a little parallelogram. A 3 forms gives you a 3-dimensional parallelepiped. And this is exactly what's happening here. You get the infinitesimal volume, which is going to be in terms of parallelepiped. And then the form gives you the mass contribution of that. and then the idea that you are integrated. And now, again, when you define forms and you go and look at a differential topology book, they're not, the words that are uttered are not mine. They're completely different, and it's very hard to see the geometrical picture. Because technically, when they write D something, that's for them is the form. And then for us, instead, the D something is the infinitesimal piece that we give to the form. And so all of differential geometry is completely obscure because they're calling the thing that we would call vector, they're calling it one form, and the thing that we would call one form, they're calling that. And it's completely backwards because, again, they want their definition of vector is this derivation thing. And it gives a completely different flavor. And again, it works for the type of stuff that they're doing. But to get to tease out the physical meaning, it's a complete. What I'm trying to do, and you see it in the book and in the stuff that we work on, we're trying to create a notation for forms that follows exactly Einstein type notation, with the index and stuff, so that we can understand what's going on in terms of components. And for the exterior product, we use this the wedge. So you know that you can imagine the gradient as the nabla applied to a scalar function. And then you can see the divergence as the nabla with a cross product of a vector field, and the divergence as the nabla scalar product with another vector. Okay, so the idea is that all these things become the nabla wedge product with whatever form that you have. So the function, the scalar function is a zero form. And now you have the nabla applied to a zero form, you're going to get a one form, which is going to be the gradient of that thing. When you have a one form, which would be a sort of, it's not really a vector field because it's a form, it's the opposite of a vector field. You make again, the exterior derivative, so nabla wedge one form, you get the two form, and that two form is the curl. And you understand the curl not as another vector field, but something that gives you two directions. So it's a function of an area, and it gives you something. Like in the same way here, the vector field is not, the magnetic field is not a vector. It's not a one form because it does not get a line, it gets an area. It gets an area, it gives you the magnetic flux. And this is where in 3 dimensions we just say, oh, it's not a vector, it's an axial vector. And then you're completely confused because you're using all these objects and you don't know what they are. And here the point is that, no, we can actually make all those things so that it follows the physically precisely, because you know that all these things are going to get some type of infinitesimal shape. And the dimensionality of the shape tells you the dimensionality of the form.
Yeah.
And so that magnetic field is about area, is about flux. So it's a two form, and non-relativistically. And non-relativistically, the electric field is something that you apply to a path. Therefore, it's a one form.
Yeah, that makes total sense. Okay, one more thing. A bivector would be a dual of a two form. Is that correct?
Right.
Okay, yeah, then that makes sense. So for me, it's like I learned everything in terms of curl and divergence because it works in components and in 3D. But of course, I think it makes no physical sense. It's much easier to not think of a cross product like as giving you a new vector, but instead a new area. And geometric algebra seems to be like extending that to all forms so that it is algebraically like uniform, I guess. But that would be like another step. Like the wedge product is physically meaningful already. And I don't know, I think the geometric product is something like a generalization to all forms.
So
that you can add them and stuff like
the
that.
metric product is mixing two things. It's mixing the wedge product with the scalar product. Like
Yeah.
that's
Okay.
the thing that it's doing. And
is physically meaningful. This is already a step up, but the next step, combining that across all forms, is physically not obvious how to interpret that.
right, because first of all, in symplectic geometry, when you talk about phase space, you have the wedge product, because in wedge product you have it anywhere you have a differentiable manifold, you have the wedge product, because you can always define the volumes. But you don't necessarily have a scalar product, because you don't have a metric tensor, you're not on a Riemannian manifold. Right? So if you're already saying, oh, I want to talk about the Clifford algebra, okay, I'm on phase space. I shouldn't talk about it, the Clifford algebra. So if you say, oh, that's the thing that I want to talk, now you're screwing yourself, because in this case you can't. So what are you going to talk about? And so it's better to keep the wedge product separate, because it's doing a geometric function, which is I am putting vectors together and taking function that one function works on these two vectors, the other vector works on these two vectors. I'm making the product, and now I have the product of volume. So I understand what's happening there. Then, if you are on a Riemannian manifold, you are going to have a way to turn forms, right, to turn covectors into vectors, because you have a metric tensor. And then what you're doing is taking the two forms that have a lower index, put the inverse of the metric tensor, and making a scalar product. Clearly, the operation is completely different than what happens in the wedge product. In fact, I still don't fully understand what's happening if I take a 3 form and I contract it with a 1 form on the other side. I don't have a good sense geometrically what is it that I'm doing. Certainly, I'm not doing something simple such as, oh yeah, I'm making a function of the volume of the two things that you're given. And so that's why, like, to me, I find it hard to believe that you would have a nice physical meaningful thing mixing the Riemannian product, the scalar product from Riemannian geometry with the wedge product. It's a nice, convenient mathematical notation. I can understand that. But again, maybe my imagination is too limited, and 6 months from now, somebody told me, oh, yes, you can think this as doing the same thing. But if you're interested when you're here to this, I would love to have to write at some point some kind of article, paper, where basically we have all these things laid out. That basically say, look, this is how you should think about these operations. These, with a translation. If you go in the mathematical textbooks, this thing is actually going to be written like this. If you go somewhere else, you do GR, when you're doing that thing, you're actually doing this thing. Because even in GR, like the fully antisymmetric thing that you use for the volume, what is it called?
Tensor, Levi-Civita.
Yes, that thing is a form. It's the volume form. And when you're contracting that thing to other things, you're essentially doing wedge product, because you're contracting with something that is fully antisymmetric.
Yeah, but it's also like coordinate dependent, right? The definition is kind of weird. I think you need a basis to define it, or at least one basis to define it first, and then it transforms or not. I don't know. It's kind of weird. Or is it?
It's the norm that it's not that it's coordinate dependent.
The norm?
Yes.
The normalization of the thing, or
the norm, like you want to, whenever you have a tensor, you can contract all the indices by itself and you make a norm.
Yeah, okay.
And the norm is, you can only talk about the norm if you are in a Riemannian manifold. There is no notion of norms of one forms and two forms and forms if you don't have a Riemannian manifold.
Yeah, so, but I was thinking at the Levi-Civita symbol. It's also sometimes called a symbol and not a tensor, because right. I think you need really a basis. to define it. I don't know if you can define it without one.
You can still define it in the terms that I had here on the slides. Like as something that you give it an infinitesimal volume and it gives you a number.
Yeah, but not like, yeah, of course, when you you first define it in one basis, and then of course it works in all the other ones if you transform it correctly.
Yeah.
But then it won't look the same anymore. Like if you would write it down as a matrix, like only zeros, minus, and plus ones.
Right. So you have essentially a real value, right? That is going to change when you change the basis. Yes.
Yes. So there's not like
that's the form.
Right? There's not one universal Levi-Civita tensor on my manifold.
Mm-hmm.
For every basis, I get another one. So this is not like the metric, which is like the same tensor every time.
So what you're basically saying is that if I just give a differentiable manifold, I don't have an absolute notion of volume size.
I should have, but it's not the epsilon, not the Levi-Civita symbol, only in one basis. Of course, then maybe there should be a volume. No, once if I have a metric, I should have a volume form.
Correct.
But something else. Okay, then we're just confusing names.
So the point is that both in symplectic geometry, you do have a volume, canonical volume, which is essentially the product of the P's and the Q's, right? So that's your volume form, and in the correct coordinate, it becomes a Levi-Civita symbol. And in Riemannian geometry, you also have a canonical way to define the volume, which is given by metric tensor, blah, blah, blah. And even you're going to get a set of coordinates for which this is one. But as a one form, right, the point is that the one form is not defined, the volume form is not defined by the actual value in the coordinate. That's going to be coordinate dependent in the same way that vectors are coordinate dependent, and the one forms are coordinate dependent. But my point was just saying is that some of the operation that you do in GR, like you know that a lot of the time you have indices that can permute, or you make a derivative minus the derivative of the other part. All of those things are wedge products that you do. There is a wedge. Whenever you have something that you're requiring some anti-commutation relation, there is some type of form or wedge product going on. And to me, it would be nice to be able to see that. Because right now you have all these a thing where you put the square brackets on one side, or I don't understand any of this. It becomes a very, I don't know if you know what I'm talking about. But.
Yeah, I totally agree. But this is not necessarily, it wouldn't be necessary to first come up with a totally new definition of derivative, right?
No,
I mean, it would be nice, but that's separate.
No, you don't need. You just need this wedge product.
Yeah. Yeah, I would love to. Like the cross product is bothering me like since 10 years.
Okay, so that I can solve for you. That's already solved.
Yeah, it's easy, but then
it's solved the differential topology with notation that it's awful, but we can actually we can fix that. So that I know how to fix.
Okay. Actually, I have an old question. I already asked you. Pure states are not corresponding to verifiable statements that we found out. And then you said mixed states also don't correspond to verifiable statements because I have like an open set around some mixed state. But if I would now average over this region, like a uniform mixture of this region, I would get a new mixed state, right?
Mhm.
Like one. Why couldn't I say, okay, I'm now in this one mixed state, which corresponds to actually like some open neighborhood of some other mixed state, and then I could verify that I'm inside that state.
Well, the fact that you know that you're inside the set doesn't mean so you're trying to put a probability distribution on the open set.
That's true.
It's a completely different thing.
Okay, so the one would say I am somewhere in the set, and the other one is saying if you repeat this experiment often enough, you will be uniformly often in each part of the set. Okay, yeah, those are two things. I agree.
And here is the issue that because a lot of people that especially in traditional quantum mechanics, they basically start saying, oh, every measurement is a probability, so that's my starting point. You can't define a probability if you don't have a sigma algebra. But you need a lattice of sets, because otherwise it's the probability of what? It's going to be a probability of a theoretical statement to be true. That's what you're saying. But then the theoretical statement is not, it has to be something else. Right? You can't always reduce everything in terms of probability. So you have the open set, and the open set is going to be a bound on the coefficient of the things that you know, which also means the probability coefficient, because you can't know the probability with infinite precision. And then within that realm, you can't know much. And then you do the things, you repeat it infinitely many times, and then you say, okay, I might turn out to be true or false, and so on. You're basically creating an ensemble, right? And so for what you're basically saying, putting a probability on the open set of ensembles, you're basically creating an ensemble of ensembles. And now you have to tell me exactly what you need, because one ensemble could be, let's say, statistical. There are actual different things spread around. One could be probabilistic. I have one thing, but many take of something. Or that ensemble could be your credence. Right? So if you have a credence on your space of ensembles, I don't think that the probability of the credence is the same as the credence of the probability. Right. The fact that I think that there is something is not going to mean that I'm actually going to see different things. Yeah. And so even though you use the same tools for probability, so how probability path, so how do you build a probability distribution over a probability distribution? It's something that, again, I thought a little bit. There is something that are confusing, but I think you need to fully specify what is the setup that you have to fully define what is it that you're talking about. I don't think it's that simple. It would be nice to have like a couple of canonical examples, which you can see, oh, you could mean this or you could mean this. Which one do you mean? I haven't stayed there and thought, how to construct that.
But have you ever seen anyone use like probabilities of probabilities? I don't know any examples.
Well, so,
okay,
so in quantum mechanics, you're already doing that because you have ensembles and then you mix them. And it's not clear, like, the probability that you can use for the mixtures can mean different things. So one of the things that I don't fully understand in quantum mechanics is that you could have an ensemble where the entropy and so on, it's really given by a process. So there is a process that is making things jiggling around, right? So it's the entropy and the mixture is really physical. It's not. Or you could have model your lack of knowledge, right? So you shoot me a photon, either one state or the other. I don't know. It's a mixed state for me. These two things that to me are completely different. Quantum mechanically look the same because you use the same mixed state. And I really don't understand how that works. There is one case where you could say that you could have two different probabilities. So suppose that you have a ball, like something where you keep taking balls out, right? And so you have a 50% of probability of taking the thing out. Or you could also say, I take one out and I keep looking at the same thing, right? Those clearly are two different things. And you should model them in different ways, right? Because in quantum mechanics, for example, you would use an ancilla system to characterize one thing, and then you're always looking at the same thing, so that you're always projecting to the same ancilla. And so there are all pieces like this that are, again, I don't feel that I finished just these pieces.
Yeah, I agree. But I've only seen one example in cosmology, which was really funny because we have a sigma 8, which is a variance of the matter density field, basically. Sigma 8. And there was one paper which had a sigma 8. And it had literally 3 indices down, 3 sigmas, because you had an error on measuring this variable, and then you had across models different, like the error varied. So you had a variance of the error of a variance. And that totally exists. But then you have, those are completely different at each level, like all the variances. So then it was still meaningful.
Yeah. So yes, these are type of things, and also the uncertainty of measurement. It's different than the uncertainty of preparation. So yeah. So right now, the way that I think about it is that I have the ensemble space. The ensemble is actually a point that represents the mixture. But then when you go and verify, you verify that again, you have prepared that thing within these limits.
Almost 1 o'clock here.
If there are no other questions, we can close it. It's just the 4 of us.
Thank you very much for doing these talks. They were really.
Thank you for you stayed here basically all the session. So
yeah.
So what do you think? Like feedback from you, I guess, would be useful.
I think I have to. So these are going to get uploaded on YouTube, right?
Yeah.
I have to go back and watch them again. There were a lot of definitions thrown out in sequence. And being someone, like I said, I did a degree about 10 years ago, and I'm just trying to get back into it now. So I'm not at the same tempo that you guys are with so much conversation. But overall, I think it's really cool. Like the basic premise of what you guys are doing, trying to draw the actual mathematical structures of basic properties of what your system should be like. It makes a lot of sense. And when I watch the YouTube videos you've got, how do I phrase this? It's you guys are looking at the parts that I never had pointed out to me when I was learning it in the university, and I've just had years of confusion that have come from the fact that I didn't really know what like the bottom part of the definition of the explanation was, and then it was just symbols on symbols and abstract definition. No understanding for you. So the fact that you guys are actually trying to do science in terms of that, I think is first of all been really helpful for me so far, and I also think is going to be very successful. It just makes sense when you listen to it.
Yeah, so it's basically my same story. I basically spent the past 25 years having these things in the back of my mind, and then was about 12, 13 years ago that things in Hamiltonian mechanics started to click. And then after that, other things started to click, and now everything is clicking. And as I said, like about especially for the formal part, 10 years ago, I didn't think it was possible, and now I see.
No, sorry. Like even just recently, I've been watching videos about geometric algebra and learning it, And it's wild to like, because it was really, I think geometric algebra at least explained a lot about linear algebra to me, because linear algebra I see now is like actually quite clunky, and some of the parts of it are pretty piecemeal historically put together. So geometric algebra was really helpful, but then to hear someone come along and say, actually, it's a very mathematical structure, you shouldn't take it too seriously. There are so many different, completely, almost contradictory views that you get when you're trying to meander through math education. I'm happy for you that it's clicked. That's very exciting. I'm looking forward to it myself. And what were you talking about? Like making some sort of dictionary? Because that feels like it would be super useful for me. That's, I think, exactly what I'm.
Yeah, as I said, I'm looking for people to help me do these things, because there are too many things for us to do.
Mm-hmm.
And I feel that I have to work on the things that. So why there are so many contradictory pictures? Because everybody's looking at the picture in a particular context.
Mm-hmm.
And the issue is that you have to find the way of thinking that can go all the way through.
Yeah.
And that's the hard part, because you have to know enough of all the different things to even just finding a notation that can span through all this is already almost impossible, because the intersection is minimal. And as I said, like you need to look at all the pieces, even the definition of differentiability. I said, no, I have to look at this because I need something that works all the way through. And so I'm like, as I said, the only way that you can do that, you have to put all these things in your brain and then synthesize and so on. And I feel that I have to do that first, because right now I am the guy in the best position of doing that.
You're right. Yeah. I do find that I think very recently I've been able to start getting like something firm that you can then base something else off of. And actually, I really think the big difference for me is that now, you included, there's a wealth of good content on YouTube. And people, especially when it comes to like geometric algebra, really good visual explanations of what's going on.
Right.
And so I can finally hold some things fixed and then some trash, which is really cool.
Right.
I also really would love to be involved in this project somehow. I know you said you're looking for people to do things. I don't know what that looks like. Like I said, I live in Canada. But if there's any way even that we could stay in touch and look at what sort of opportunities I could.
We can schedule some other meeting and see what I need to know what you can do essentially, and then we can try it.
Okay. Is your like email on your website or something, or could I?
Yeah. So if you look at me, I'm single named, the curse of the internet. If you look for this, I'm just the only one in the world. So I'm very easily findable.
Cool.
And plus you're in Toronto, so you're actually closer to us than we're in Ann Arbor, Michigan. You said you're in Toronto, right?
I'm in Toronto.
Yeah. And we've actually been accumulating contacts in Toronto and trying to find
Oh, okay.
an excuse to go up and talk to different people. So we're in the Toronto area between Waterloo and Toronto, and the Perimeter Institute for Theoretical Physics in Waterloo also nearby. And some philosophers of physics as well are in the area, as well as theoretical physicists. So.
Cool. Yeah, definitely. I'll reach out to you.
So we're done.
I think.
All right.
Thank you so much.
Thank you so much, and thank you for the people who actually are going to watch this on to the end on YouTube. I guess we put it here. Bye, guys.